Okay, classmates, it's Tuesday, finally, and we're about to wrap up or come to a conclusion about DC motors. This is a schematic that you're all familiar with by now. It's a shunt-connected DC motor. We have the shunt circuit, which contains the field winding. And then we have the armature circuit, which contains the armature, right, power supply. And, of course, we throw in both circuits, we throw in the resistance of the copper wire and anything else we need to model this circuit. What I would like to focus on now is this section right here. We've been talking about counter EMF. And I would like to conclude that as well as I can without rushing it. And I'd like for you to have a thorough understanding of what I'm about to tell you now. A motor acts like a generator when its armature rotates within the strong magnetic field of the shunt coil. Okay? So, what you need to remember, what you need to commit to memory is that this armature, this rotor, is always it's always immersed in the magnetic field of the shunt winding. Remember, this is the biggest winding in the motor. It can develop a strong magnetic field with a small amount of current. So, let's say we put this motor into operation. It comes up to speed. The rotor develops a counter EMF. The counter EMF, let's see if I've got a pencil I can write with that is suitable. The counter EMF opposes the power supply of the armature. So the counter EMF is negative, positive. Okay, so I've got a negative on this side opposing the negative of the power supply. Now that counter EMF, we normally talk about it as being dependent upon the speed of the armature. Okay, so when the motor is under normal load and it comes up to speed, we have a counter EMF, a voltage that opposes the power supply of the armature. But this voltage will never get as high as the power supply for the armature itself is, okay? Just a law of physics, because we have to have current flow, so some voltage is dropped across the copper wire found in the circuit. Now then, if you recall, if I put the shaft of this rotor under load, it will slow down. And when it slows down, its counter EMF increases. Its counter EMF decreases because it's not rotating within the magnetic field of the shunt as much as it was. So current picks up from the armature power supply, okay, and the voltages balance out, and we're back at steady state. As a motor, anytime you load that shaft and slow it down, because its counter EMF drops off, the armature circuit current increases. So when you load any motor, slow the shaft down to any degree whatsoever, it will draw more current. Good deal. Good deal. That's the motor conversation. Now then, I'd like to focus on one more thing. The counter EMF developed by the rotor depends upon the speed of the rotor and the strength of the magnetic field created by the shunt winding. Okay, so let's say my motor is rotating at 1,000 RPM. If I decrease the magnetic field created by this shunt coil, okay, then the counter EMF of the rotor, okay, will decrease. Okay. What happens is a natural phenomenon, okay. If I decrease the magnetic field right here, the counter EMF drops down, but the rotor will increase speed in order to regain the counter EMF. Okay. This is known as, this is a phenomenon known as, right here, field weakening. We can increase the operating speed range of a shunt connected DC motor by changing the strength of the shunt magnetic field. All right. This is not a freakish thing. It's been around for a long time. Our friend Tesla knew about it a long time ago. Engineers have known about it for over a century, and we use it to our advantage. Okay. Okay. Remember that this only applies to a shunt-connected DC motor. By weakening the shunt field, I can increase the operating speed of the DC motor. Okay, let's talk about field weakening. Okay. Field weakening is a technique that allows us to take our DC motor, which we would normally operate at 1,150 RPM, on up to 2,000 RPM. Now we can adjust field weakening to operate between 1,150 and 2,000. Let's say we could take it and set it for 1,500 RPM if we so desired. Now then, the way that we do this is we have to weaken the shunt field so that the magnetic intensity produced by that field is less, requiring the rotor of the DC motor to have to run faster to generate, okay, the desired counter EMF. So in a weak field, or a weaker field, a rotating device will have to rotate at a higher speed in order to have the effect of induction, electrical induction, okay, to generate its counter EMF. So it's quite simple. Just remember it like this. If I weaken the shunt field in order to generate a counter EMF that I once had with a stronger field, I have to rotate my armature faster. Now the way I do that, I look down here at the field connections. Okay, remember I can run this field at 240 volts, or I can run it at 120 volts. So, what I'm going to look at now is I'm going to look at my amperage going through the shunt. Okay, and if I reduce it, let's look at this configuration right here. If at 120 volts on the field, or at least for this schematic, if I drop my amperage from 10.3 amps to 3.3 amps, at 3.3 amps and 550 volts on the armature, with the current no higher than 226 on the armature, my motor will turn at 2,000 RPM.